Okay, thank you for having me here today. Give me this opportunity to present my work and the work of our group. I would like to start with some moment that maybe makes happy someone's, maybe not so happy another one. And this is the 2006 FIFA World Cup final. So, some special fact about this final is that the attendance of this final was around 70,000 people. So maybe some of you are asking now, what does that have to be with the stroke? The interesting point here is that if you consider these 70,000 people, this doesn't even cover the half of the case of a stroke per year in a country like Italy or France. So that's the point. Now, I'm David Rodriguez, and today I'm gonna talk about microwave imaging for brain stroke monitoring. First of all, I would like to thank you some of my colleagues from different universities and the funding of this project. So, is the stroke important? Let's see. 1 in 6 people will have a stroke in their lifetime. More than 50 million people worldwide have a stroke every year. And the stroke is, in fact, the second cause of death just behind the heart disease. So it is important. So, but what is the stroke? The stroke is a medical emergency that occurs when the blood flow to the brain is interrupted for some reason. So the two main categories and reason for that are, in one hand, is a block. So one artery is blocked, and this is called the ischemic stroke. The second reason could be a burst. So an artery or a vessel just burns and the blood goes out. This is called the hemorrhagic stroke. These two category types of stroke cover the 95% of the stroke. So what we have to do in case of a stroke? In fact, you have to act fast, as fast as you can. Because what? Because time is brain when we are talking about the stroke. One interesting thing is, like, for each minute that you don't treat the stroke, you are losing millions of neurons. From all the people that have a stroke every year, 25% die. From then, 50% is gonna have a disability that could be permanent, so have some problem. And only 25% of these people will have a full recovery. And one of the reasons of that depends a lot of the timing. So as fast as you can treat a stroke, is higher the probability that you full recover. So right now, the two main diagnosis imaging techniques used for clinicians are MRI and CT scan. They are very reliable techniques and they are the gold standard right now. But still they have some problems. They could be expensive, they are bulky, so you cannot use it in the bedside. And it's difficult, for example, put them in an ambulance. And in the case of CT scan, this is it is harmful because of ionizing radiation. So what we are proposing is a complementary technique that is called microwave imaging system. We don't want to replace the current techniques. We want to complement with a system that is able to do a follow-up, that's it, in another word, that monitoring in a continuous way the stroke, that you can do it with the previous one, and also with a small factor. So you can put that as our system in the bedside or in an ambulance, in a helicopter, something like that. The general idea of the system is gonna be like this. We're gonna have a bunch of antennas all placed all around the head, and we wanna try to identify the stroke that is inside of the head. But let me go a little bit slow here. For starting, microwaves. It's in the title. So what is microwave? We are talking about the electromagnetic waves. So the electromagnetic waves, you can imagine like a wave, like the light that we see every day. They have a different frequency. And microwave are a special band of frequency that is signaled here in green. In our specific case, we're gonna be working around 1 gigahertz. So what is the special thing about this frequency band? The special thing is that in this frequency band, when we irradiate, we impinging some field on the brain, the response of the tissues of the brain respect to the tissues of a ill tissue like the stroke present an electric contrast. So at the end, this contrast is gonna scatter it's gonna generate some field. But again, let me explain this point maybe with an analogy is a little bit easier to explain. So to explain this scattering phenomenon, let me start from the bottom. Imagine that a pool, you are next to a pool, and you just are in the corner of the pool, and you with your finger or with your hand, you generate a wave. This is something that is called, let's say you are generating a field that we're gonna call the incident field. Now that imagine in the same point, you are generating the wave, and for example, a child is now in the middle of the pool. So this child in the middle of the pool is generating a deviation of the field that you are generating. And this deviation is what we call the scatter field. So imagine for a moment that you take the initial case, that the incident field, and the field when you put the child, and you take this, subtract these two effects, and you're gonna get the response of the child. So the child is gonna see, or the object that we're gonna study is gonna be like a small source. So we can see here in the top right of your screen. And this is what we wanna do. With this scatter field, we wanna know how is the object inside the pool in this case. So I hope you understand that. So again, come back to our system. We're gonna have some antennas that they are generating the field, like in the example with the pool, and another antennas that we are receiving the response of this. But the thing is, like, what we actually measure is the total field. We cannot measure the scatter field. And this is also something that is called the non-linear ill-posnet problem. But I'm gonna go in that later. So imagine now that you have an antenna. Let's say this is the purple point in the left square. So the antenna is radiating, but you cannot actually measure in all the space. What I mean is that you have some sensor around the head, but you cannot go inside of the head and put antennas inside of the head. It's not physically possible. And with this measure that you are taking outside of the head, you want to reproduce what we call, like here, like you see in the right, the scatter, but in our case, it's going to be the stroke. So this is something that is called the inverse problem. And let me again try with an analogy. Imagine that you are preparing, you are a chef, and you are preparing some recipe. You have the ingredients, you have the recipe. So you take the ingredient, the recipe, and you do a dish. In this case, I present in, you are doing arepa, a typical Colombian dish. When later, imagine that you don't know how to do the arepa, this special dish. You taste it, and someone say, okay, now give me the ingredients. You never tried before, and you don't know the recipe. It's not so easy. This is the inverse problem. So in one way, you go from the ingredient to the dish. In the other way, taking a measure, let's say that you take a taste of the dish, you want to come back to the ingredients. And this is what we call the inverse problem. And this is very difficult to do. Now, for do that, we are using someone called an imaging algorithm. In our case, there are different algorithms, but we are using someone based in a differential scheme. So what I mean with a differential scheme, we want to take measures in different time. Let's say we have a reference scenario, T0, and a different scenario, T2, that could be a scenario 2 hours later, 2 minutes later. And we want to do the subtraction between the measurement of this time, in different time. But you can think why we are doing that. And I don't want to go deeper in the mathematical point of this, but I'm just going to mention 2 things. For solve this problem, we want to use first something that is called the distorted Bohr approximation. And what is behind that is that we want to assume that the effect and the field that generate the difference is very small. So we want to assume that this field is in Dept. We can approximate that like our reference scenario. Because of that, we can then linearize the problem. And also we want to use something that is called the truncate single value decomposition. That is another algorithm where you get the main parts of your data, and you just truncate the data. You just get the main part of the information and get another part out of the problem. And with that, you regularize the problem. But we can move in this later. So our aim is get something like this. We want to get something from the diagnosis to the treatment, and we're going to do the evolution on the follow-up of the stroke. Indeed, this is a need in the medical field that is not resolved right now, because if you go to the hospital with a stroke, usually you just get an initial diagnosis, but the hospital is not able to do a continuous monitoring of that for many reasons. For example, the MRI is just one machine, and there are many patients and they cannot do it that continuously. Also, an MRI could be spent several minutes. In this time, how we said before, the time is brain. So let me describe a little bit our system that we have in our lab. It looks like this, like in the bottom, but for easier understanding, I just show here this like a diagram. So we have a PC that is gonna be the main control, and this PC is gonna be connected to a switch control and a VNA. The VNA is a vector network analyzer. Imagine that is an equipment that sends some signals and receive the response and give you a number. So in a general way, this is a vector network. We also have a switching, because this vector network analyzer, they have only 2 ports. So we can just send one signal and receive one. But we're actually using a big number of antennas. In our case, 24 for antennas. So we need a switching that just use 2 antennas at a time. So in general, it's gonna be board like this. The computer is gonna communicate with the switching matrix. The switching is gonna say which antenna is transmitting and which one is receiving. And the information is coming back like a small piece of information. Later in the computer, you get all the information and remake or reshape the matrix like a 24 by 24 matrix. With this information and using this information as input of our algorithm, we are able to produce 3D image. That this is a mapping of what is inside of the brain. Here is a clarify that we don't have the same resolution that have, for example, an MRI, and we don't are reproducing all the tissues. We are only reproducing, or we are focusing in the imaging of the stroke. So let's see some examples. Okay, this should be, that was a video that is not working, but this is our system. Each one of these blocks is one antenna, and the antenna is like a planar antenna that is immersed in a block of material. This material is called the coupling material or the matching medium material. You can ask for what is that? And that is because if you want to penetrate in a better way the head, you need to have a material that have similar the electric parameters that the head. The head have different tissues, so they have different parameters. But let's say that we take an average and we do a material, an artificial material that is do it with powder, graphene, and glycerin, and that is a solid block that mimics in a way the condition of the brain. With that, we generate a better penetration of our wave. If we don't use this, the result is like you try to impinge some wave, but all the energy is coming back and we don't get any penetration. So that's the reason. Some results that we get is something like this. In this case, we put some, this was a simulation case where we put a target and a stroke. In this case was an hemorrhagic, if I don't mistake. And we are doing the follow-up, like the stroke start like a half sphere and later just grow out in one direction, and it makes like a capsule. So after that, we start to do measurements in the lab using a simple model of head. It's something like the head that you see in the bottom, and we fill it up the head with brain liquid, like what we call average brain liquid. So we take the properties of the brain and we make a liquid that makes the average properties of that. Later, we put some target with the properties of an ischemic stroke or an hemorrhagic stroke, and we put it in the middle of the head. We run our algorithm and we get the position and in some way the shape of our target. In this first approach, we use for testing because it was easier initially, and plastic sphere. Later, we move in the last week to a more realistic scenario. So instead of this, we take a calf brain. So in fact, you take 4 calf brain, and we shape it like a human brain. Later, we take this capsule, the yellow one. Imagine that's the capsule, the kinder capsule. And we put a liquid that is mimicking the blood in the case of the hemorrhagic or the properties of the ischemic. Later, we put this in the phantom, like you see in the right-hand side of the screen, and we take the measurements. Some of the preliminary results that are gonna be published very soon. We were able to localize the different, we were able to localize either ischemic and hemorrhagic stroke in different locations. So the take-home message is first of all, this technology that we are proposing is just a complement of other technologies. is a contactless, non-invasive, portable, and totally safe for the operators, and it's potentially real-time. That what is very, very important in this case. For sure, we have some limitation that is like the spatial resolution. We are just only starting. This is a very emerging technology, so we have limited clinical trials, and we are in developing. But maybe the important measure is that remember that the time is brain. I am not a clinician, not even a doctor, but in some case you feel that you are feeling something like a stroke, just go as fast as you can to the doctor. Thank you very much. If you have questions, don't hesitate. You can contact me as now or send me one email. I would like to also thank you, the European Union, for funding this project, and the Emerald project. That is a European consortium working in biomedical application using microwaves. So you can get more information there. Thank you very much.
Thank you, David, for your very interesting talk. We have some questions also for you.
Thank you.
The first one is a curiosity. It's just a curiosity. Does the imaging system consider Raman scattering? Does possible electromagnetic fields generated by the matter with frequencies that are different from the incident one?
Sorry, I don't get the question.
Does the imaging system consider Raman scattering?
Consider what? Sorry?
The so-called Raman scattering, which is which generates radiations with matter that are reflected fields, which have frequencies that are different from the incident one, the frequency of the incident wave.
Okay. For sure, when you are we are radiating a 1 gigahertz. We are also trying with different frequency. When you talk about these other frequencies that depend if they are in the band of the antenna, we are using a monopole that is the band is very close, so it's just 200 megahertz, around 1 gigahertz. If it's something in that band, it could be affected, but if it's out of the band, the antenna acts like a filter, so it's not a problem for us. For sure, also see if you are thinking about maybe the coupling between the antennas, we consider that, and we avoid to use the information of the antenna. If we are transmitting with one antenna, we are not considering the antennas around that antenna, for avoiding the coupling between them.
Okay, thank you. Then we have another question that requires the apparatus that you showed us previously, and people ask which is the time duration for having a whole measurement of the brain, like days that you showed us previously, of the whole brain.
Oh, good. Yeah, that depends on different things. Now we are just prototyping this, so we are taking a threshold very high. So our measurement of all the system could be spent some minutes, around 10, 15 minutes. But this is a prototype, and for sure this could be lower, around 2 minutes. In fact, there are another a PhD student at Politecnico de Torino who is working right now in accelerating this process using a FPGA. So,
okay, thank you.
With that in mind, we can get in the range of minutes, like one or 2 minutes instead of 15 that is right now. So it could be like a real time. And the other point is like the stroke is not like a grow out very fast. So 1 minute is more than enough for us. It's not like the stroke is gonna grow from 2 centimeters to 10 centimeters in just 1 minute. It's not like that. It's slower.
Perfect, thank you. Then we have a final question. May this system be used to prevent hemorrhagic stroke?
No. Our aim is not to prevent. It's just we start from the point of the diagnosis, so the stroke already happened. So we are not focusing in prevention. We just try to have a system that could be used as fast as the doctor can. So we are thinking something that you have the system that you put in the ambulance, because the first hour after the onset of a stroke is the crucial one. So if you treat a stroke in this first hour, it's highly probable that you recover from the stroke. But the problem is, like in a city like Torino, a big city, the time that you spend, you call the ambulance and you go and the ambulance gets you home and come back. Later you are in the hospital. In this time you spend around 3 hours. And in these 3 hours, you lose the time, and for that you can die or you can have a disability for the rest of your life. So instead, if you can put this in the ambulance and you can start to do the diagnosis in the first 30 minutes, is something that is going to save your life. It's going to save money for the hospital, because you don't have to stay in a recovery time for many months, because the recovery time of this is not 1 week, 2 weeks. It could be years. So this is something like we are aiming.
Okay, thank you. I do not see any other questions, so